Hello, everybody. My name is Chris Matthieu, and I've been working with Intel for, 4 or 5 years on various IoT uh, projects, and I've lately been doing a lot of thinking about supercomputing. What could you do if you had millions of small IoT devices out in the field that could all see each other, communicate with each other, and compute for each other or ask for computes of each other? Kind of like this supercomputer mesh network thingy I've been prototyping called computes.io. So that's what we're here to talk to you about today. The concept around it, how it works, and from a developer perspective, how to use it. So we're looking for feedback. Before we get started, if you look at this slide, this is an interesting slide that I've pondered quite a bit about just the sheer number, volume of IoT devices coming to market. And if you look at this, we're still in the middle of this hockey stick curve, looking at connecting, tons of sensors. I mean, home automation is exploding, driverless vehicles are exploding, industrial IoT has been getting more and more interesting. If you look at where 2017, you're looking at a lot of switches, then you're looking at a lot of power outlets coming up next year. All the SOMs, I mean, like all of the Intel Edisons, etc. The Arduino 101s, very successful products, millions of those devices sold to date. But what's really interesting is by 2020, as you can see from this slide, a lot of the analysts are predicting 50 billion with a B connected IoT devices in the marketplace. So I can't help but think, kind of like my Mac here, that 80% of the CPU on all of these devices are pretty much idle all of the time. When you look at like typically sensors, I mean, they're streaming analog or digital bits of data, sometimes periodically, sometimes they're waking up and chirping every 15 minutes, and the rest of the time they're generally idle. Or take an idea of like the Edison, out in the field. There's a lot of processing power on the Edison, very small device, and it would be a shame not to maximize the CPU capabilities of 50 billion of these connected devices. So this is what's interesting. What I see, a lot of early IoT platforms started in the cloud. You look at Azure IoT, even Octoblue, which was the platform we built. All of these there's a shift, as more and more IoT transactions, machine learning necessities, AI capabilities. Those all are moving to be as close to the computing device as possible for a few reasons. I mean, one, for sheer volume of data. The edge is basically everything that's not cloud. Edge is everything that's where the device lives. If it's a driverless vehicle, it's the vehicle itself. The sheer volume of data that's coming off of these sensors and the sheer necessity of machine learning, analyzing that data in near real time and making decisions on it. I think the car is a great example. As you look at these self-driving vehicles, we're near the ASU campus, and we've got three driverless vehicle manufacturers, from Uber to Google Waymo to GM, driving around and actually picking up people around the ASU campus. These cars are making thousands, if not millions, of decisions a second. And they do not have time to relay that information to the cloud, make a determination in the cloud, and relay that result back down to the edge or the vehicle itself. So the cloud was not really ever designed to do that. I mean, if you kind of think about the way the cloud computing works, it's really good for collectively harnessing and aggregating lots of data, being system of record, et cetera. Its throughput speeds are mostly optimized for download, not upload. So the sheer latency of making those decisions or streaming, massive volumes of data don't really work well for cloud computing endeavors. So it's becoming more and more important to have this computing on the edge or as close to the device as possible. And that's really what I've been thinking about and experimenting with computes.io. Really, this concept of taking these idle CPUs and GPUs on all of these IoT devices, these 50 billion IoT devices, and kind of blurring the line between cloud and edge to the point where everything computes. And let me show you what this looks like. So there's kind of four pieces of this. We've created a private mesh network where all of the nodes can identify themselves and swarm together basically in a private network. So for instance, a driverless vehicle might be in and of itself its own mobile data center, its own private mesh network. If you wanted, you could maybe say all the Uber vehicles near the ASU campus are also part of a private mesh network where they can communicate with each other and pass telemetry data between each other to let them know, hey, I'm a minute behind you. I can get that. I can pick up that person instead of you, to be more efficient. Each one of these computes cores, if you will, you can look at them each as being a node on the private mesh network. They also they can request work. They can request computations from other computes cores near them on the network, or they could even do the work themselves if they have computing capacity available. The computing capacity, as you can see here on the slide, it runs as JavaScript applications in a sandbox. So very similar to your web browser. JavaScript runs in your web browser. It does not access the local disk or the local memory of the machine. That's the same way computes jobs work. They run inside of a JavaScript container sandbox on the device. We also leverage a technology called IPFS, the Interplanetary File System. Perhaps you've heard of it. It's a great open source project for doing all of our peer-to-peer file system and file sharing across all of these nodes. So that's very efficient. If you kind of think about this in the IoT edge environment, we don't need any infrastructure. Each one of these nodes, as I mentioned earlier, is both a kernel and a core. It can both request computations and do computations. It can share data sets as input or output data sets as IPFS file hashes peer-to-peer with each other in this mesh network. And one more point here on the slide is that they also, using IPFS again, we're using the PubSub capabilities of it. We're able to create a signaling layer or a messaging engine, if you will, across all of the nodes on the mesh network. So you could kind of think about that as not only could they communicate to say, hey, I've got it, or I'll pick up that next person, but you could also look at this from a machine-to-machine messaging capacity. The days of needing like an MQTT broker store for PubSub is no longer necessary. So that's all baked into the computes core. And as I mentioned there's also some cool Node.js machine learning tools also built in the core, most specifically the brain.js project. So you guys can look at that. And by the way, I've got a couple of demos coming up. So if you have your web browser handy, you can join in on the fun and participate. So hang tight. This is kind of what a compute's infrastructureless environment looks like. I mentioned earlier, it's all peer-to-peer, so you can see each node of computes can run on basically every operating system, from Linux, Mac to Windows, as well as iOS and Android, as well as browsers, which get very interesting from just loading computes.js in an HTML file and having browsers around the world participate in both requesting computations and doing computational work. So very, very similar in the structure in this diagram here. Everything's a mesh network, and regardless of operating system, all of these compute nodes basically act like a single machine, like one computer. Sounds kind of wild, but these are some cool things that we've been doing with this. So if you take just an example of these Raspberry Pis, you can do the same thing with Edison's or any of Intel's processors. I've kind of been experimenting building Beowulf computers, and you could build your own. I've got instructions at beowulf.computer, the web address. We've got the ability where you can take disparate processors, even like SOMs, like systems on modules, like the Edison, and put these all together. So if you look at these Raspberry Pi 3s, for example, there's 4 of them duct taped to an Ethernet switch, and each one of these Raspberry Pis is a quad core processor. So in essence, what you have here, when you run the Computes API against this Beowulf, you'll see it thinks it's a single machine running 16 cores. So that's 4 cores times 4 gives you 16. So we've experimented, as you can see from these photos. The one on the left is 20 Raspberry Pis. Unfortunately, these were the version 1 version, so they were only single core. But not only could you like take the one on the left and have a 20 core Beowulf, and then take the one on the right that I just showed you as a 16 core Beowulf, but you can connect them to the same network bridge, and now you've got 36, 16 plus 20 cores. So it's really infinite how you can continue to connect disparate machines into a bigger and bigger and bigger Beowulf, if you will, supercomputer node. And these can work over the internet, so they could be global, or they could work, just purely on the edge, like we in the earlier discussions. Just for early validation, I wanted to see, does this really work? Like, I took the 9,000 factorial, wrote a quick little Node.js or JavaScript application, as you can see on the left, running in a single thread, on my MacBook. And it took 7 seconds, to loop through, it's 1 times 2 times 3 times 4, that's what a factorial is. Looping through that computation, 9,000 times took 7 seconds. If you look at the code example on the right, I essentially broke that up into 3 jobs. You can see the for 0 to less than 3 loop there, and it basically takes that same computational formula and passes along the data parameter there to create 3 jobs, each doing 3,000 factorial, and then adding up or multiplying the sets of numbers up together. That took 2.2 seconds. So as you would expect, 7 seconds for one core, 2.2 seconds for 3 cores. It kind of maps out pretty closely to what you'd expect if you just break this problem up. So in essence, early on, we were excited to see that we were onto something. This is kind of a more modern code example of what this could look like. We have a computes node module that we'd be happy to give you guys access with to experiment with. But you can basically require computes in your code, join a private network by passing in a key on the connect, which I don't have. It defaults to a public network if you don't pass it in. And then you could see, you could just run computations, and like in this particular instance, we're trying to find the largest prime number. And you can just kind of say, let's run 10,000 massively parallel requests, evaluate, is the number prime? Is it currently the highest prime in this parallel function? And then at the very end, map reduce this down until we've done this, 10,000 times, and identify the highest prime number found. So kind of a fun example to play with. This is where we get to the point where if you have a web browser I would love for you to participate with me. So we'll see how many people are online here in a minute. So I'm going to go to this demo.computes. I would encourage you not to yet. I'm going to give you a URL that you can join in, but we're going to watch what demo.computes.com does. We're going to find a password. Like we're going to give it a password to hack. Let's say Intel. Usually 3 letters are really fast. 4 letters take about a minute. I'm not sure what a 5-letter will take, but let's just see. And obviously, the more participation you guys have, or the more browsers that you guys do with cores, that will crack this password faster. So what happens is when I hit go. Actually, let me start a worker here. You guys go to https://demo-core.computes.com/ and this is important that we're all in the same session together. It's JICO. So demo-core.computes.com/JICO. It's kind of a random 4 letters we choose, but I'm gonna add that worker. So what we'll see here is my worker is listening to this dynamic queue called JICO. It's not getting any work at the moment. That's what my dashboard's going to do. It's going to farm out work, and it's saying that I have 4 cores in my MacBook here that are all available for computations on computes. So I'm going to hit go. What's going to happen when I do that is it's going to create the MD5 hash of the word Intel, and then it'll start distributing work across as many cores as you guys have joined in on this demo. And the more cores, the faster it'll brute force attack this demo. But it's basically going to go through every combination, create an MD5 of that example of that combination, and then check to see, is it the MD5 of this password I'm entering here. So I'm going to hit go. I'm curious to see how many of you are participating, because this dashboard will give us the count of the number of cores that are online working. There, it's kind of setting things up. Let me toggle to my worker, see if it's getting anything yet. So not yet. Setting things up. So this is an example of computes.js running inside the web browser. So we're using the web browser of all of my cores and any of your cores that are participating to help us crack this password. Okay, I'm starting to see some active jobs there. Well, it seems like it's taking a little bit longer than normal to come back. So maybe we've got a lot of cores joining. Maybe it's just setting up the jobs. You know, what's funny is I haven't actually tested this demo beyond 3 or 4 people sitting at the table. This could be interesting. Well, now I'm really curious how many cores you guys are throwing at this. Oh, there it goes. Okay, so now look here. Okay, so this is better. So now we're seeing 8 cores, so 12 cores. And you can see it's showing you the current guesses, and then it's also showing you the attempts. We're up to 13, 14, 15,000 guesses per second. That's pretty awesome. And this is the most I've seen, 16 cores. That's awesome. It's keeping a timer there as it's walking through all of these. So it's taking it's a brute force, a classic MD5 brute force password attack. But what's cool is it's distributing this work across all 16 of these cores. Wow, 24 cores. This is getting exciting. Don't normally do 5 letters. I'm not sure how long this takes, but I think we're getting close. Like I said, usually a four character is about a minute. 5 gets a little bit more interesting. This is also getting interesting. So let me explain kind of a little bit about the topology of this platform. So the original experiment started kind of as a cloud architecture, so centralized and distributed. This particular version is running decentralized and distributed, but it's kind of quasi decentralized. And what I mean by that is the kernel, kind of what we've dubbed the kernel, is the core that's requesting the work. And in this case, it's this dashboard. This web browser Oh, snap. It fell over. This web browser is, yeah, I don't want to restart it for the sake of time. You guys can play with this. I'll tell you what, maybe let's do a quicker one just for the sake of time. What this one's doing is that the kernel itself is, it looks like it's still got some other jobs in the queue. The kernel itself is actually the one distributing the work across all of the core. So the browser itself is responsible for distributing the work. Okay, there we go. So that took 20 seconds to do a 3-character MD5 hash. Maybe I should have started with that. Anyhow, the next version we're experimenting with now is basically the network. Basically, would be in charge of distributing the work. So we wouldn't need the kernel, to be responsible for all of that communication. You could basically submit a job saying I need 1 million of these computations, and then go to sleep or go offline. So that'll be very interesting to watch. Let me go back to the presentation here, because I think this kind of gets interesting in the concept of capabilities. When I ran this NovaBench application on my MacBook, it said that my MacBook is 273 gigaflops. That was the calculation it did. Supercomputers are measured in flops, floating point operations per second. My MacBook is equivalent to 273 gigaflops. What's interesting is if you look at the top 500 supercomputers in the world, there's one from Bull called the Manny, and its throughput is 430 teraflops. I mean, if you did the kind of the one-to-one calculation, in essence, if you had 1,577 of these MacBooks that were running, at full capacity of computes, they would be equivalent to the same 430 teraflops of the Bull Manny supercomputer. And if you just Google top 500 supercomputers, you'll see this list. Number 500, which is the slowest one on the list, is 530 teraflops. What's interesting is you look at this supercomputer in China, the Sunway. It's at 93 petaflops. So you could imagine, if you had a whole office full of computers, 20,000, 30,000 desktops, you might be able to get to this to be at that level or greater. So kind of interesting. Let me show you one more type of example, and then I'll stop and take some questions. So if we start up the IPFS daemon, this is what's going to do our private mesh networking. It's going to do our pub sub, and it's also going to give me a file system, if you will, for computes to move input and output data around. In this tab, I'm gonna actually run a kind of a loop application. This example is going to be in Node.js instead of the browser. Well, let me show you. It's very similar how it works. If you guys are familiar with Node and JavaScript, we're going to require the computes npm module. We're going to join the computes domain name. And if you wanted to pass in optional parameters, you could specify maybe a single node as being the IPFS gateway if you wanted to. In this particular instance, it just assumes that each node knows how to communicate with IPFS, and that's that daemon that we're running. We're going to do a quick little loop where we're going to loop 1,000 times. We're going to pass in a JavaScript computation to each one of these nodes 1,000 times, where we're going to say the value coming in is going to be we're going to iterate, from 1 to 1,000. This 1 to 1,000 times, and we're going to say the result is equal to the iterator parameter times 123. And what's interesting is that there's an on-result event that fires every time the kernel requests the compute and a core picks up the work and returns the answer. It's going to fire this on-result. All we're going to do here is we're going to console log the results. We're going to make sure we loop 1,000 times, and then we're going to terminate the job. Other demos I've just looped forever and kicked off the job again, but you kind of get the gist. Let me show you how this works in Node. I'm going to run it in debug Node, just so we can see all the output. And there we go. So we'll see this machine start acting as the kernel, start connecting to computes, waiting for other machines to join. It, like I mentioned earlier, it itself can also be the core and the worker. So it's actually sending this particular looping request out to all of the nodes on the computes network. And I think I have a machine at home that's an 8-core machine that's probably picking up on some of this results. Oh, we unable to find a worker. That shouldn't have bugged. Anyhow, let's run it again, and then we should start seeing results here in a moment. There we go. Sending work to various machines. Then we should start seeing results coming back. Let's try this one more time. I had updated the computes node module right before this. Typical developer. Sorry about that. Let's see. Yeah. Anyhow, so I should probably say this is highly experimental. I tell you what, I'm gonna reinstall the computes node module, and we'll come back to run this example again if we have time. And in the meantime, I'm going to go back to our app here to see if you guys have any questions for me. So we went with JavaScript because it was a pretty easy language to sandbox, kind of like a browser sandbox is JavaScript. I'm curious if you guys that are online now on this webinar, if that's a familiar language for you. I'm trying to see like kind of votes like +1s or thumbs up if you like JavaScript. Otherwise, maybe list the programming language of your preference. That'd be good for me. Yeah, the question about the examples, I think the password cracking example is just a good one that everyone understands because that one's very simple to massively parallelize. One of the interesting things we're doing now, I mentioned brain.js is now baked into the computes core. Is we're starting to experiment with Python. Cool. We're starting to experiment with sequential computes operations. In other words, the way machine learning works, it likes to go kind of sequentially. Like take a game, for instance, or teaching a robot how to walk, or it has to go through like a lot of the same iterations to train a model. Golang, cool. So that's kind of interesting. I'm seeing other languages like Python and Golang. One of the things we've talked about is if we use Lua, for instance, as our core sandboxed language, we could transpile from JavaScript and Python into Lua, and we could probably package it up in a Golang app that would be even smaller than a Node app. So that's kind of interesting. Yeah, and Python at IoTagger, I think Python's an interesting one because of all the machine learning projects that are coming to market. You know, like the TensorFlow and Cafe from Facebook. So that the only issue is with the C++ bindings. I'm not sure that would transpile easily to Lua, which would make us start looking at more like Docker-like containers and things like that. Which that's cool too, but it just takes a little bit longer, to fetch, a Docker container via IPFS, even if it's peer-to-peer. You're dealing with just bigger file sizes at that point. Let's toggle back and see how this is working. Okay, so it's done. So let's try this again. Just curious if that helped. So again, this is the looping through 1,000, looking for nodes. Let's see if this works. I want you to see some results start coming back. This is where it kind of fell last time. Yep, same thing. I must have broke something right before the demo, so I apologize. Cool. Oh, compute sensitive. What is that? Let's see. Let's make this smaller. I'm just curious if this runs if I just make it 10. Okay, so that worked. At least this gives you a better idea what I was trying to show. So you can see each result set coming back with the answer, and then I'm just iterating. These aren't the parameter that was passed in. This is more on the result side, just counting to make sure we got 0 through 10. But what's interesting is you can see the request that goes out with the computation. If I scroll up, and then you can see the results that come back on the results file, and you can see that there's a clock on each one, so it's counting the milliseconds elapsed on each job. So you could kind of do some calculations on how efficient your network is running. This is an example of what it looks like when a core receives some work. So as you can see here, every core on the network has a machine ID, so it knows from which machine ID to which machine ID. There's the broadcast channel that it's messaging for the pub sub. There's the job ID, and there's the operation that the looping is sending it. And then you can see from the data input coming in, this particular one was iterator 9 that is sending into that computation. And you can see there's the results of it coming right back. Otherwise, that was pretty much it. I'm always interested to hear your feedback. If you think of something even after this webinar, feel free to email me, chris@computes.com, and I'll get back to you on that. And this feedback that you provided was beneficial, the Python, the Golang, and I was super excited to see us hit 32 core count on the demo. Thank you very much for attending my webinar. Hopefully you learned something and it was fun for you as well. Start thinking about, as your companies get to the point where you're needing more compute power on the edge, rather than deploying more data center like hardware at the edge, this could be an interesting alternative solution for you. Okay, so chris@computes.com. Love more feedback. Thank you very much for attending. Thank you.